Hey everyone. Here's going to be the next type of test we can apply to a certain type of series. So far we've looked at the test for divergence, which like I said, usually that's the first test you should try to look at just to see if you can quickly tell if a series diverges or not. We've looked at p-series. Those are very easy to tell whether they converge or diverge. And then we looked at geometric series, which are a specific class of series. The geometric series really are the only series we have so far where we can actually tell specifically what number they're going to converge to. With all the other tests we have, we can just tell if the series converges or diverges. So now we're going to learn yet another test, and this is called an alternating series test, and it's used when we encounter what's called an alternating series. So an alternating series is if we have something like this, -1 raised to the n out front, um, multiplied by some sequence a sub n. So the effect of this -1 to the n out front means that when n is equal to 0, that's just going to be 1 because anything besides 0 or infinity, which is raised to the 0, is going to equal 1. When n is equal to 1, it will be -1. When n is equal to 2, it will go back to 1. And when n is equal to 3, it will go back to -1. And it's going to just keep bouncing back and forth between 1 and -1. So the effect is that when we write out the series, we have a positive term followed by a negative term followed by a positive followed by a negative, and so on and so forth. So the effect that this has is that if we apply it to certain series, we could actually have a series that if we just looked at a sub n, that sequence itself, when we put that into a series, it would be a divergent series. But when we add this alternating component to it, it actually becomes a convergent series. So alternating series are kind of interesting in that way. Sometimes this -1 to the n, that could also be represented as, let's say, if we had cosine, and I'm doing my best to write well with the mouse right here. If we had something like cosine of n times pi, that would also be kind of equivalent to -1 to the n, because when we add in 0, that will be 1. But when n is equal to 1, it will be -1. When n is equal to 2, it will go back to 1, and so on and so forth. So sometimes if you see trig functions that are functions of n pi out front, that's also an indication of an alternating series. And we can actually just replace this with -1 to the n or -1 to the n plus 1, depending on where our series started. But anyway, it's a very simple test. So basically, if we identify that sequence a sub n, we first want to check, is that series always positive? The next thing we want to do is say, okay, is that series decreasing? Meaning, is each subsequent entry in the sequence lower than the one before that? And then finally, we want to see, okay, well, does the limit of that sequence as we go to infinity equal 0? And if all these conditions are met, we say the series is convergent. If one or more of them is not met, then we actually can't say whether the series converges or diverges. It turns out in that case, the alternating series test is inconclusive, and we actually have to do a little bit more work. So let's look at an example. So if we have this series right down here, see if you can identify that sequence a sub n and go through those 3 criteria in the alternating series test. Okay, so if you did this, you should have come to a sub... Whoa, that was a good voice crack. Okay, we should have come to a sub n is equal to 1 over n. It turns out, remember that 1 over n itself was called the harmonic series, which was divergent? Well, if we add a -1 to the n plus 1 in front of that 1 over n, it becomes the alternating harmonic series, which actually converges. So this is what I was saying on the previous slide, where sometimes when we make divergent series alternating series, they become convergent series. This is one example of that. So if we look at all 3 criteria, well, every single entry in 1 over n is positive. Every single entry in 1 over n is decreasing, meaning that when n is 1, it's equal to 1. When n is 2, it's a half. When n is 3, it's a third, so on and so forth. And a half is less than a third. I'm sorry, a half is less than 1, and a third is less than a half. So every single entry in this series is always decreasing, so it meets criteria number 2. And if we take the limit of 1 over n as n goes to 0, as n goes to infinity, we get that that limit would be equal to 0. So by the alternating series test, this is a convergent series. So let's try one more. All right, see if you can apply the alternating series test to this series right here. Okay, it turns out if you do this one, we'll get in this case a sub n is equal to n squared over n plus 1. And even if you look at the first couple terms, if you compare when n is equal to 0 to when n is 1 to when n is 2, you will see that this is actually not a decreasing series. When n is equal to 0, we're going to get 0. When n is equal to 1, we get 1/2. And when n is equal to 2, we will get 4/5. So what you can see, whoops, maybe I want to write the other side of that 4 right there. But as you can see, 1/2 is greater than 0 and 4/5 is greater than 1/2. So this one violates this second term in the alternating series right here because it's not decreasing. But it turns out if we actually went to evaluate the limit of a sub n, we would also get that's equal to 1. So that violates condition number 3 of the series. So 2 of the conditions in the alternating series were violated. So remember, the alternating series does not tell us whether something converges or diverges if it's inconclusive. It's just inconclusive and we'd have to do more to it. It turns out if we try to do the test for divergence, which in this case would be evaluating the limit of this whole thing that's inside the summation, we would actually find that that limit would be an undefined limit because we can break it up as to the limit as n goes to infinity of -1 to the n multiplied by the limit as n goes to infinity of n squared over n squared plus 1, which would end up just being something that alternates between plus or minus 1 multiplied by 1, which obviously is not going to be equal to 0. So it turns out if we just did the test for divergence on this in the first case, we would get that this series diverged. So this is a divergent series, but it's important to note that it also failed 2 of the criteria of the alternating series test, but that's not what made it a divergent series. It was doing this test for divergence which allowed us to say that the series was divergent. So that's it. Alternating series, pretty simple. It's just kind of like the p-series. Anytime you see a -1 to the n or a -1 to the n plus 1 or a cosine of n pi, sine of n pi, something like that, some number that's going to bounce back and forth between 1 and -1, you pretty much should always think first to check this alternating series test to see whether these types of series converge.